In this example, we'll sketch the graph of the rational function 2x squared plus 2x minus 4 over x squared minus 6x plus 8. Like the other examples, we will need to find the y-intercept, the x-intercept, the vertical asymptotes, and the end behavior. To find the y-intercept, we need to look when x equals 0. So evaluating our function at 0, we get 2 times 0 squared plus 2 times 0 minus 4 over 0 squared minus 6 times 0 plus 8, which is negative 4 over 8, which we can reduce to negative 1/2. So we get that the y-intercept is the point 0, negative 1/2. For the x-intercept, we want to look when y is 0, or our function is 0, which means that we need to solve the equation 0 equals 2x squared plus 2x minus 4 over x squared minus 6x plus 8. But we've seen before, we can multiply both sides of this equation by x squared minus 6x plus 8, leaving us with just 0 on the left and 2x squared plus 2x minus 4 on the right. So we just need to solve the polynomial 0 equals 2x squared plus 2x minus 4, which we can do using the quadratic formula. If you'd like to see the steps done out, you can click the link to the left now. Using the quadratic formula, we find that the solutions are x equals 1 and negative 2, which means that we have x-intercepts at the points 1, 0 and negative 2, 0. To find the vertical asymptotes, we need to look when the denominator is 0. That is, x squared minus 6x plus 8 equals 0. Here, we can solve again using the quadratic formula. If you'd like to see the steps of this done out, you can click the link to the left now. Solving x squared minus 6x plus 8 equals 0 with the quadratic formula, we get that x equals 2 and x equals 4 are our vertical asymptotes. Finally, we need to understand our end behavior of this graph. That is, what happens to our function as x gets very large, either going to positive infinity or to negative infinity. As we've seen, polynomials act like their lead term for large values of x. So our rational function, 2x squared plus 2x minus 4 over x squared minus 6x plus 8, simply acts like 2x squared over x squared, which can be reduced to 2 over 1, which is just 2. So for large values of x, our function looks like the line y equals 2. We call this a horizontal asymptote. Now, like polynomials, we need to check if our function is positive or negative on some of our intervals. Because we know there are no more x-intercepts, so our function f of x can only change from positive to negative, or vice versa, at our vertical asymptotes or at the two x-intercepts that we already found. Now, to the left of negative 2, we know as our x values get larger and larger, they approach the line y equals 2, so the y values must be positive. Between the points negative 2, 0 and 1, 0, we pass through the point 0, negative 1/2 at the y-intercept. Since this y value is negative, all of our y values between negative 2 and 1 must be negative as well. On the right end of our graph, we again know that our function needs to approach the line y equals 2. As we approach the vertical asymptote at x equals 4 from the right-hand side, our function is either going off to positive infinity or negative infinity. But since there's no way of crossing the x-axis again, since we have no other x-intercepts, our function cannot be going to negative infinity at x equals 4, so it must be going to positive infinity. This again is because we know our function approaches the line y equals 2 on the right-hand side. What remains to be checked is what's happening to our function between our x-intercept 1, 0 and our vertical asymptote x equals 2, as well as what's happening between our vertical asymptotes x equals 2 and x equals 4. To start, we'll check a point between 1, 0 and x equals 2. We'll try x equals 1.5. Evaluating our function at 1.5, we find that f of x is roughly 2.8, which is positive. So since our function is positive at 1.5, our function must be positive for every x value between 1 and 2. Because if there was a value of x that it was negative, we'd have to cross through the x-axis again. But we know we don't. So this means our function is going to approach positive infinity as it heads towards x equals 2. Lastly, let's pick a point between x equals 2 and x equals 4. Say x equals 3. Evaluating our function at x equals 3, we get that f of 3 is negative 20. So since our function is negative at this point, our function must be negative for all values of x between 2 and 4. Otherwise, we'd have to cross through the x-axis again. So this means that at both of our vertical asymptotes, x equals 2 and x equals 4, our function is going off to negative infinity. Because again, our function can't become positive without having another x-intercept. So using all of this information, we now have the graph of our function f of x equals 2x squared plus 2x minus 4 over x squared minus 6x plus 8.